everybody. Welcome to section 2.4, where we are going to talk about the precise definition of a limit. So far, up to this point, we have used the intuitive definition of a limit. Intuitive meaning when I say limit, feels like something that you need to approach, which is what we've been doing. But now we want the mathematically rigorous definition of a limit. So this section will be not too long since it really only focuses on this one concept. So I'm going to give you the definition and we'll work out a few examples. You'll notice that in this section specifically, the solutions will not be, not a whole lot of like numerical calculating. It'll be a lot more writing, traditional writing in the sense of, you're explaining exactly what you found, coming to a conclusion in the end. So first we'll start off with the definition. Let f be a function, or f of x, if you will, defined on an open interval containing the number a, except possibly at a itself. What that means is f is a function. It's defined on some interval and has a starting point and a stopping point as far as the interval is concerned. It's defined in there, but it might not be defined at a itself. We saw that limits also work if there's a hole or a vertical asymptote. We could still talk about this concept of a limit. So that's all that little last part is saying. We say the limit as x goes to a of f of x is equal to the number capital L, is what the book likes to use, if for every epsilon positive there exists a delta positive such that if 0 is less than the absolute value of x minus a, which is less than delta, then the absolute value of f of x minus capital L is less than epsilon. And that's our definition. Now, right off the bat, epsilon and delta, these are coming from the Greek alphabet. And in mathematics, whenever you see this epsilon, we use epsilon to represent a very small quantity. So epsilon could be a very, very teeny tiny number, but it's always used to represent a positive number. I guess I shouldn't say always, but it's just something that we basically all agree on. Whenever we use an epsilon, we're talking about a really, really tiny positive quantity. So what does this mean visually? We kind of understand what limits look like. Let me draw you a picture here, and we'll call this our function f of x. And let's say that this function f of x is defined on some open interval containing a. And again, it might have a hole in the graph, but we could still talk about a limit as x goes to a, or it might have a vertical asymptote there, but we could still talk about a limit as x goes to a. So that's what this little stipulation is, except at a itself, possibly. Well, that means that if I look at this function as x approaches a, it should give me a limit of L. So as x approaches a, I'm finding the limit to be L. Based on the epsilon delta definition, that means that given this small positive quantity, epsilon, it sort of gives me a window to look at. in terms of L plus a little more epsilon, or L minus that little bit of epsilon, it forces me to look in this window, but because delta depends on the epsilon chosen, I might get A minus delta or A plus delta in terms of showing that this limit is actually going to be equal to this value L. Now, this is pretty key here for every epsilon positive. Right? Keep note of that wording, for every epsilon positive. That means someone could come along and say, try this smaller epsilon. And as that window starts to shrink, and maybe this will make a little more sense if I sort of extend this out a little bit. Maybe this will make a little more sense if I sort of extend this out a little bit. So notice that you're stuck inside this little box region here. You're basically stuck in this little region. And if someone comes along and says, haha, I found a smaller epsilon, then you need to find a delta that works and keeps you within that little box. And if you can't do that, then the limit does not exist. And it's definitely not L. But if you can do that for every epsilon, no matter how teeny, tiny, tiny we make this window, as far as epsilon is concerned, up and down, we can always find delta small enough that keeps us in that window, left and right. And that's because delta, our choice for delta, is going to depend on epsilon. So epsilon's like the boss, right? You don't get to pick epsilon, right? You have to show it for every epsilon. So epsilon is the boss and says, I need this, do it by Friday, right? And then it's up to us to come up with a way to work that out and get it done by Friday. So epsilon's the boss. You're not picking an epsilon. You have to show it for every epsilon. We can choose delta, right? There exists a delta. It is our job to find it. And if we cannot find a delta that gets this done for every single epsilon, then obviously the limit would fail. So I'll draw you one more picture and then we'll jump into some examples. And that picture will be, let's take a function that maybe goes like this, and then it goes like this. All right, and who knows what that function is? Maybe it's just some piecewise function. You can see I'm not even really picking any numerical values here. I'm just saying this function is defined on an open interval containing A, maybe not at A itself, but in this case it actually is because we've got this solid point here. Now let's see what happens when we say, okay, we should be able to find a limit here. That means that as I pick some sort of limit, notice I could choose this as a possibility for L, maybe this as a possibility for L. The left-hand limit as x goes to A would leave me hanging down here. The right-hand limit as x goes to A would leave me hanging up here. And you'll notice that I can now shrink down some sort of possibility for L plus epsilon or L minus epsilon. And I will never, ever be able to find A plus delta or A minus delta, no matter what. Look at the box that I'm restricted to. My function does not even exist there. So even if I had some sort of guess for L, whether it be this one up here, well, then I could shrink around that point and I wouldn't be able to find a delta that works, that keeps me within that box. Or I could come down here and try and shrink around this point here, but then I lose the right side limit. Right? And for that limit to exist, it has to exist both from the left and from the right. And if, of course, if I try and stick it in the middle somewhere, well, then I lose both the left and the right limit. Right? So here's a situation where it would fail no matter what happens. Oh, and I wrote 3's. How about that terrible bad habit, right? We don't want to write 3 for epsilon. Right, so no matter what my choice for delta, someone could always come along and give me a smaller epsilon, and I will lose this. Now, maybe someone could give you a very large enough amount of space to work with, and you could try and really fight it, but it has to work for every epsilon, right? You can't come back to me and say, give me a larger epsilon. No. I will give you an epsilon that's 10 times as small if you tell me that, because it has to work for every epsilon. So, throwing around this word epsilon and this word delta, they're just symbols that we use. And they're coming from the Greek alphabet, because we tend to have already used most of the letters from the English alphabet already. So, let's take a look at a problem here. It says prove that the limit as x goes to 2 of 4x minus 5 is equal to 3. Of course, using the epsilon delta definition. Right? It doesn't just say find this limit, it says prove it, and we want to use this rigorous definition. It's easy to find if we plug in 2, right? Because we could just say 4 times 2 is 8 minus 5 is 3, thus the limit must be 3. And the last section we saw that if this number is in the domain of this function, then that's how we can find that limit, simply by plugging that number in. Well, I already told you the limit. Now I'm telling you to prove that that is the limit without a shadow of a doubt, which means we'll have to rely on the definition. So, we're going to prove it without a doubt using epsilon and delta. So first I'm going to say, and this is how we should start pretty much every epsilon delta style proof, is let epsilon positive be given. You don't pick epsilon, right? I'm not picking epsilon. I'm saying it has already been given. It could be the teeniest, tiniest little number that we have to respect. So I'm stuck with respecting that teeniest, tiniest little number. And then we'll come up with a delta that is related to that epsilon, so that no matter how small you make that epsilon, you inherently make the delta even smaller as well. And it will still work. So that's our job. We want to find delta positive such that, and we'll go back and we'll look at the definition, if 0 is less than the absolute value of x minus 2, there's my a, in this case it's 2, is less than delta, then the absolute value of f of x, which in this case is 4x minus 5, minus L, in this case is 3, is less than epsilon. All right, go back to the definition. I'm just basically setting this up based on that last line of the definition. I have to find the delta that works for every epsilon, so that if the distance between x and 2 is another way you can say this. When we talk about absolute value on the number line, we're basically talking about distance. The distance between x and 2 being less than delta implies that the distance between the function and the actual limit, capital L itself, will stay less than epsilon. All right, so that's how that works. Okay. Notice that. Now we're going to do a little bit of manipulating with this piece. Right? When we work through these proofs, we set it up like this, and then we just do a little bit of manipulating here. 4x minus 5 minus 3 inside the absolute value is the same thing as saying the absolute value of 4x minus 8 is the same thing as saying the absolute value of 4 times the quantity x minus 2 is the same thing as saying, well, multiplying by positive 4, whether I do it inside or outside of the absolute value, I'm still multiplying by positive 4. Only x could give me a positive or a negative sign that I would need to fight with. So I can pull that 4 outside of that absolute value. what I'm after here, right? I want to keep the absolute value of x minus 2 less than delta, but it needs to depend on given epsilon. Notice I've basically isolated this absolute value of x minus 2. This means that we choose, and again, we get to pick the delta. We choose delta is equal to epsilon over 4. That extra multiple of 4 being there might make us too big, so I want to divide by that 4 when I pick my delta. I want epsilon over 4, which is a much smaller quantity than just epsilon itself. So I'm going to make this choice for epsilon, or sorry, this choice for delta. Okay, still with me? And I'm going to keep on trucking. I'm going to say we're choosing delta equals epsilon over 4, so that if the absolute value of x minus 2 is less than delta, then the absolute value of 4x minus 5 minus 3 is less than epsilon, which implies that if the absolute value of x minus 2 is less than delta, then the absolute value of 4x minus 8 is less than epsilon. I'll put a period there and I'll say, this implies if the absolute value of x minus 2 is less than delta, then the absolute value of 4 times x minus 2 is less than epsilon. This implies if the absolute value of x minus 2 is less than delta, then 4 times the quantity of the absolute value x minus 2 is less than epsilon, which implies, and I'm trying to show you every step here that's getting me to if the absolute value of x minus 2 is less than delta, then, and this is an inequality, I'm going to divide by positive 4, then the absolute value of x minus 2 is less than epsilon over 4. So now we've got basically our choice for delta has been exposed. And now we can basically summarize and say, thus, if the absolute value of x minus 2 is less than delta, then the absolute value of 4x minus 5 minus 3, which is equal to the absolute value of 4x minus 8, which is equal to the absolute value of 4 times x minus 2, which is equal to 4 times the absolute value of x minus 2. That must be less than 4 times delta. Why? Because delta is larger than the absolute value of x minus 2. Right? So this absolute value of x minus 2 is just some number, and it's a positive number because I'm taking its absolute value, which means delta is a little bit bigger. So now when I replace the absolute value of x minus 2 with something a little bit larger, then I get to use this inequality. But notice that we chose delta to be epsilon over 4. So now I'm going to replace this. This is equal to 4 times epsilon over 4. Multiply by 4, divide by 4, that's just epsilon. And you can see what I've just shown now. If the absolute value of x minus 2 is less than delta, then there's our function minus our limit L must be less than epsilon. And that is the definition. Right? We have to show that if the distance between x and this number 2, in this case a is equal to 2, is less than delta, then our job is to show that the distance between f of x, which is 4x minus 5, minus L, which in this case is 3, is less than epsilon. And so I'm going through a little bit of algebra here to try and get to this inequality, which is ultimately what I need. Now I can, if I would like to, rewrite this last statement as this thing is less than epsilon. Right? I have shown that. And now we're done. And we can do one last little summary if we want. We can say, therefore, the limit as x goes to 2 of this function 4x minus 5 must equal 3. Because we've satisfied the definition, so that has to work. Quite different, right? That's a quite different type of problem than you've seen before. And in calculus, you encounter a lot more writing, or at least you should encounter a lot more writing, especially if you're focusing on proofs. And you have to do a lot of explaining. So again, just to kind of brush over it one more time, epsilon positive is given to you. You don't get to change that because epsilon could be anything. It has to work for every epsilon. We have to find the delta. At some point, we need to choose the delta. But we write down the definition with our a plugged in, our f of x plugged in, the capital L limit that they give you plugged in. We write down this definition. Then typically we start to manipulate this piece here to expose how this could relate to epsilon. And we do that by just doing a little bit of algebra, a little bit of factoring. Positive 4 multiplied inside could be pulled outside the absolute value. You're still multiplying by positive 4, whether that positive 4 is inside or outside. And then now we can see how delta will relate to epsilon, because here is absolute value of x minus 2 restricted to less than delta. Here is absolute value of x minus 2. If I divide out by 4, I get a smaller delta than epsilon. Right? Because if epsilon's positive, I can divide that positive number by 4 and get an even smaller number. So that way, every time you say, here's a much smaller epsilon, my delta is always smaller than your epsilon. And you say, okay, well, my epsilon's the smallest epsilon you can think of. And I say, okay, my delta is 4 times smaller than that. And so no matter how hard you try to make epsilon this teeny tiny window, you'll always get a smaller window for your delta, meaning you'll always find this limit. And then it's just a lot of restating the facts that you've just found with this manipulation. You're restating that once you get to this point where you've found x minus 2 in absolute values is less than delta, then you get the less than to pop up by replacing that with delta. And then, of course, delta was chosen to be epsilon, so you show how it relates to epsilon. So let's do another one. And that wasn't even really a terrible function. It was a linear function. So there wasn't too much going on with that one. Let's pick on something else, like perhaps a power function that I chose. And that is to prove that the limit as x goes to 3 of x cubed is equal to 27. Again, 3 is in the domain of this power function x cubed. I could simply cube 3 and get 27 and say there is the limit. But now we want to prove using the epsilon delta definition. So again, if we're writing out a proof with epsilon and delta, first thing to start off saying epsilon positive be given? Right? Someone could give you any epsilon positive, so let it be given. Right? Let it be known that someone has given you an epsilon that you need to satisfy. Then we want to find a delta positive such that, and some people do omit saying delta positive, epsilon positive. It's understood that they're positive, but I still like to throw it in there just in case. We want to find delta positive such that we, basically fill in our parts if 0 is less than the absolute value of x minus 3 is less than delta, right? There's our a. In this case, a is 3. That's the limit we're going towards. X is going to 3. Then the absolute value of f of x, in this case is x cubed, minus capital L, in this case is 27, must stay less than epsilon. Right? I'm just filling the parts that were handed to me from the problem. I'm just filling them into the definition. Right? I haven't proved anything yet. I've just basically stated what I have to prove. So now my goal is to prove it. So first, we'll play with this, right? Just like we did with the last problem. We'll play with this x cubed minus 27 in the absolute value. I'm going to say, notice that the absolute value of x cubed minus 27. This is a difference of cubes, right? This is x cubed minus 3 cubed in the absolute value. So I can do a little bit of factoring, kind of like what I did in the last problem, but in the last problem I just factored out a constant multiple. Here I'm going to factor using the difference of cubes. Go review that if you need to, but this is how the difference of cubes will factor down. Since it's a difference of cubes, there's x minus 3 as my first linear factor here, and then I get this irreducible quadratic factor. And so now I have these two different factors. I don't have a number that I can just pull out. I don't want to say that, I'm going to choose delta to be epsilon over x squared plus 3x plus 9, right? So this is giving me a little bit of a headache right now, because x can vary, right? It's a variable. So I have to introduce like one more step that I need to fight with this x squared plus 3x plus 9. Since we want x to go to 3, based on our choice for a, we look at 2 less than x less than 4. Right? I want x to go to 3, so I'm just basically stating to the reader that I'm going to stay between 2 and 4 because it's close to 3. Our job is to get as close as possible to 3, so I'm giving myself plenty of space to work in. Right? I'm giving myself plenty of wiggle room here, which is totally fine because we're never going to look at 2 or 4 for this proof. We really want to get to 3. So I'm giving myself a little window, plus 1, minus 1. That's not my delta. My delta is not 1, right? I don't want to pick that because then someone could come along with a much smaller epsilon and maybe my delta equals 1 is no longer good enough to prove it for every epsilon. I'm just saying that let's look close to 3 right now to see if that helps us find a good delta. So we're looking between 2 and 4. One other thing I want to say about this function x squared plus 3x plus 9 is because x squared plus 3x plus 9 is strictly increasing on the interval 2 to 4. Right, we'll use the open interval 2 to 4. We don't actually need to use the 2 or use the 4, basically. Let me not finish that off. I'm going to say comma. We know that, pull my values out here. So I went ahead and just calculated these ahead of time. 19 is less than x squared plus 3x plus 9 is less than 37. Where am I getting those numbers from? Well, because this quadratic is strictly increasing from 2 to 4, its smallest value will be attained when x is equal to 2. And because this quadratic is strictly increasing from 2 to 4, which is the window that I'm looking at, then I know that its largest value it will ever attain will be if x is actually 4. Now again, I'm concerned with 3, so it's going to be somewhere between those two values. This is a strictly increasing function. When x is 2, I get 19. When x is 4, I get 37. So I know my values will always stay somewhere in between there. So I know my function values will always stay somewhere in between there because x is staying somewhere between 2 and 4. So what that does for us is now that tells us that this piece, x squared plus 3x plus 9, as I look close to 3, I'll stay less than 37, right? And that's giving me plenty of wiggle room to play with. I could pick an interval that's even big or even smaller, like 2.5 to 3.5, but I just didn't want to fight with the fraction or decimal or whatever. So sticking with whole numbers makes it just a little bit easier. Since this is the largest value this can attain, I'm going to have absolute value of x minus 3 times 37 at the maximum. Then that's how I want to choose my delta, so that I get the smallest epsilon satisfied. So we choose delta is equal to epsilon over 37. So that if the absolute value of x minus 3 is less than delta, then the absolute value of x cubed minus 27 is less than epsilon. And now we just play around with it, essentially. Thus, if the absolute value of x minus 3 is less than delta, then absolute value of x cubed minus 27 is, and here we are, now we're going to show this statement and prove this. We're going to say this is equal to the absolute value of x minus 3 times x squared plus 3x plus 9, because that's factoring this out using the difference of cubes. So those are my factors for x cubed minus 27. But this is going to have to be less than delta, because x minus 3 in absolute values is less than delta. Well, maybe I'll do one more intermediate step here. I'll break it up so you get absolute value x minus 3 times absolute value x squared plus 3x plus 9. Right? It doesn't matter if I multiply these two numbers together and then take the positive version, or if I multiply two positive versions, I still get the positive version. But this maybe helps us break it up a little bit so that, see this quantity, x minus 3 in absolute values, that has to stay smaller than delta, which means if I replace this absolute value x minus 3 with delta, I get to use the inequality. Because this is a much smaller quantity than this. This is larger over here on the right. And then this piece, at most, is going to be 37. When I look at that little window. Obviously, as I get closer to 3, it gets smaller, but I'm making sure I satisfy this for every epsilon because we chose delta to be epsilon over 37. There was our choice. We chose epsilon over 37 for our delta, which means we just use the definition to show that if the absolute value x minus 3 is less than delta, then absolute value of x cubed minus 27 is less than epsilon. And that is the definition. So now we're good. And again, we can just kind of summarize it in one last sentence. Therefore, the limit as x goes to 3 of x cubed must be 27. So again, just to kind of brush back over it a little bit, epsilon is a given small quantity that we have to obey. Our job is to find a delta that relates to that epsilon so that it fits the definition of a limit. We played with this around a little bit, but instead of getting a numerical multiple that we could just easily divide out to come to this nice little trick here, we had to do a little fighting with this quadratic because it's a quadratic, so it takes on different values. This isn't strictly a fixed number. This could change because it depends on x. Well, we looked at x within a certain amount of reason, right? Here's 1, 2, 3. So we basically just said, you know what, we're going to look between here and here. Your epsilon's going to be really, 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 really small. So rather than start in this huge window and work our way down eventually to your really, really small quantity, I'm just going to start pretty close. So somewhere between 2 and 4. And because this quadratic x squared plus 3x plus 9 is just strictly increasing, that allows me to shove it between its two outputs. 19 when I plug in the number 2 into that quadratic. When I plug in the number 4 into that quadratic, the maximum I get is 37. So I know I'm stuck between those two output values for that function. So that's why I want to pick this delta to be as small as possible. Epsilon over 19 is not as small as epsilon divided by 37. Right? Dividing by a much larger number gives me a much smaller delta. And I want to keep my delta small so that it satisfies every epsilon ever. And then I just simply show that, as I write it out, it fits the definition. There's some algebra going on there to expose the working nature here, but this does work out so that if absolute value x minus 3 is less than delta, then absolute value x cubed minus 27 must be less than epsilon, which fits our definition perfectly. Again, different. It's a lot of reasoning. Use your words. But mathematically speaking, in terms of like the algebra or the arithmetic that's going on, there's not a whole lot. But we did come across situations where, if we looked at the limit of a function, and maybe there was like a vertical asymptote there, when we looked at the limit, it might shoot up to infinity or something like that. So I want to do one example where that may be the case. But first we'll give you the definition, because it's just a little bit different because, rather than use epsilon, which is typically epsilon is a very small positive quantity, when things tend to shoot up to infinity, there's no ceiling there. So they want to use a very large number to represent that. So they'll change that just a little bit. But most of the definition remains the same. Let f be defined on an open interval containing the number a except possibly at a itself. Right? It doesn't have to be defined at a in order for there to be a limit at a. Then the limit as x goes to a of f of x equals infinity if for every, and this is where they'll change from epsilon because they want to represent very large quantities. For every, and the book just uses capital M, greater than 0, there exists a delta positive such that if 0 is less than the absolute value of x minus a, which is where x is going to, is less than delta, then f of x is greater than m. So you can see this changed a little bit from the previous definition where we talked about this, this number capital L for our limit. Now we're saying that the limit as x goes to a is going to shoot off to infinity. And analogously, you can change this to show that the limit as x goes to a of f of x equals negative infinity. And rather than rewrite the whole basically definition again, the book chooses an n rather than m. They use n and show that the function is always less than that n that is chosen there. Because negative infinity, so we want a very small, we want the function to stay smaller than any n given. Rather than rewrite the whole definition, it is basically ditto word for word, except when it goes to negative infinity, you want f of x to be less than n. Right? So if this is negative infinity, then you want f of x to be less than some positive quantity n. That's the only thing that you change. Right? Rather than show it's much larger than everything, you show it's much smaller than everything because the limit's negative infinity. So again, rather than rewrite the whole definition, that is the only tweak. Let me find my eraser here. So again, we use epsilon for a small quantity. That's why they just basically changed this to some letter to represent a very large quantity. So let's pick on an example. Let's say we want to prove that the limit as x goes to 0 of 1 over x squared is equal to infinity. So, our proof. Not using epsilon this time, we're going to say let m positive be given. We want to start out by saying, hey, someone just handed us this very, very, very large number. We want to find delta positive such that, again, just kind of going back to the definition I just gave you, 0, let me write if 0 is less than the absolute value of x minus, in this case, a is 0, right? So I'm writing the absolute value of x minus 0 just to expose the a. You could simply just write absolute value of x, but then someone might look at you like, why are you writing that? So I'm kind of just exposing myself here and saying that x minus 0 is x minus our a. In this case, our a is 0. So if the absolute value of x minus 0 is less than delta, then, going back to the definition, 1 over x squared is greater than m. No matter how large this capital M is, I can show you that my function is always larger. Right, so again, I have to pick delta. M is already the large quantity that has been chosen. Right, so I don't get to pick capital M. It could be gigantic and then some, but I'm going to show you that my function stays above that value. It's even greater than that, which means it must be going towards infinity. As you increase the capital M and my function stays above it, well, my function goes to infinity faster than the whatever large finite number you can provide. So again, now we start to do some play. I'm going to say, notice, 1 over x squared greater than capital M means that x squared is greater than 1 over M. Actually, I'm sorry, we're taking reciprocals here, right? If this quantity, this reciprocal, is larger than capital M, then x squared must be less than 1 over M. So we're going to choose our delta here by taking a square root on both sides and saying that x is going to be less than, and since m is a positive number, 1 over m is a positive number, so I can take the square root of this positive number. All right, so again, if this number is very large, larger than m, then the reciprocal is very small, smaller than 1 over m. So now we're going to choose. We choose delta equals 1 over square root of m. I'm going to write 1 over square root of m because square root of 1 up top is just 1. So it just makes it a little easier to write that square root. So that if the absolute value of, again, I'm writing x minus 0 instead of just absolute value of x to sort of expose that a that we're talking about. If absolute value of x minus 0 is less than delta, then one over x squared is greater than m. So this is the definition that we wanted, and it's the definition that we can achieve. So when we let delta equal 1 over the square root of m, well, we basically get our definition. I don't know, I'm trying to think of something more to say, but I'm just going to say, therefore, limit as x goes to 0 of 1 over x squared must be infinitely large. So as x goes to 0, 1 over x squared goes to infinity, which makes sense based on the graph if you look at it. Because we've got this asymptote there. Now again, infinity is not like a finite number, so I'm not claiming that this is some sort of capital L. By saying that, this goes to infinity, I'm basically saying that the limit itself does not exist. And if you look at a function like 1 over x, where it might go to negative infinity on one side, positive infinity on the other side, you may want to break this down into, two separate one-sided limits. So it kind of depends on the function. Whereas this one we can get away pretty cheaply simply by stating that, no matter which side it goes up to infinity. So we just pick a nice capital M that's very large, and we show that our function stays above that very large value. So again, just to kind of brush back over it, Given this very large quantity, capital M, our job is to find a delta, so that if the absolute value of x minus 0 is less than delta, then this function 1 over x squared stays above this capital M, very large value. And then we just basically want to play around with it till we can get to the point where we find a delta that gets the job done. All right, we'll let delta equal 1 over the square root of M. So that now what we're saying is, if the absolute value of x minus 0 is less than delta, which, when we start off looking at the definition, if 0 is less than the absolute value of x minus 0 is less than delta, what this basically allows us to say is that, 0 is less than the absolute value of x is less than delta. Well, this is positive. We don't even need the absolute values. So this tells us that x less than delta tells us that x squared is less than delta squared. Tells us that if we take reciprocals, right, if this thing is a small number and I reciprocate it, then it becomes larger than delta squared reciprocated. Which tells us that since I've chosen this delta, to be 1 over the square root of M, I can rewrite this as 1 over the square root of M, quantity squared. Right, because I do still need to square that delta. Which, when I simplify this out, and I'm sorry for running out of space here, 1 over x squared is going to be greater than, this is 1 over M, which is M. Right, and I kind of left that out of the proof because it does look a little messy with all the deltas and the m's flying around. But if this is satisfied, I get just the absolute value of x here. I can drop that because I know it needs to be positive, so I'm looking at positive x. I can square that, reciprocate that. When you reciprocate, though, you have to change the inequality the other way around, and then replace my delta with my chosen 1 over square root of M, but it still needs to be squared, so I square it up. And then, of course, I'm doing 1 divided by a fraction. We don't divide by fractions. We multiply by the reciprocal, M over 1. So I do keep my function above this very large value, M, which satisfies the definition. And that's it. That's really all I wanted to walk through in this section. Just doing a couple proofs, maybe more than a few proofs, in order to get you guys hopefully a little comfortable working through these. Now the section says that to do 1 through 31 odd. This is one of those cases where it may take a bit more practice to get used to it. Start off with the nice linear functions by replacing a in the definition, f of x in the definition, capital L in the definition, and work through some of the linear functions. Then maybe move on to like an x squared function. Then maybe move on to an x cubed function. I did an example with an x cubed function for you. And just kind of build up your confidence as you go. But as you write, try and remain to the same structure of let epsilon be given. We need to find da-da-da-da-da. If this, then this. We do a little bit of manipulating. We choose our delta. Now we show that it works by replacing things with delta and staying less than epsilon. And then once you work through a bunch of them and start to know the flow, then it becomes a little easier. The first couple of times you write the proof, you're going to be doing it one line at a time. Then you're going to scratch your head and go, what do I do next? But as you work through more and more proofs, at some point, trust me, you do get to the point where you know how to do an epsilon delta proof. But sometimes there's tricks to them. Sometimes they can be a little tricky just depending on what the function is. You'll notice I didn't do anything with trig functions, and that's just based on time and things like that. So let me know if you have any questions. Otherwise, I think we'll just cut that section off there, and I'll jump into 2.5. Not in this video, but the next.